Hello and welcome to the video. And until now, we saw that if we have a delay in our system, basically a delay in negative feedback loop, it can be modeled by using a delay in its feedback path like this and applying a step down input. Let's say like we had a stable input and our output was stable, and now we step down the input to 0 volts, and that's how when we apply a step down input, we have our equation, which is like dv naught by dt equals to minus omega u by k v naught as a function of t minus td, and at tau equals to 1 by e, basically sigma 1 is equals to sigma 2 equals to minus e times omega u by k. So basically, this is the fastest response without overshoot, and this we derived in our previous video. So now we have to analyze for the values of tau which are greater than 1 by e. So because until 1 by e we had no overshoot, but now we have to realize the same for the values of tau which are greater than 1 by e. So as always, we'll consider our equation, and now instead of real, we have to consider complex solutions. As we discussed in last video, we have no real solutions after tau equals to 1 by e. So basically, let's say v naught now will be some parameter which is scaling factor times exponential of some complex number times t, and thus when we take dv naught by dt and put our value of v naught over here as well, which is this value, this equation comes out to be this equation basically, and these two values cancels out each other, and we are left with this equation. And after solving it further, when we get it in a form of real plus minus imaginary, so we have real part and the imaginary part, and we equate the two corresponding parts, and by that we will get two equations, one for the real part and one for the imaginary part. And when the like to do the sanity check, let's say the time delay is 0, and when td equals to 0, we will get the value of our sigma as minus omega u by k, and our omega will be 0. So that's how we do the sanity check. And now by considering or normalizing these values by omega u by k, our sigma prime comes out to be this value, omega prime comes out to be normalized omega, and tau comes out to be the normalized time delay. So basically our equation looks like these. So we have these two equations, and now we have two non-linear equations, and this is not possible to solve explicitly. So we can analyze the nature of our solution, and by analyzing the nature of our solution, we can set up boundary conditions for the time delays. So let's see the nature of the solution. Basically, we have our v naught like this, and there is something in the brackets with exponential. So for positive value of sigma, the overshoot keeps growing and growing, and for negative value of sigma, the overshoot keeps falling. So this is the basic law of exponential, and thus we need to find out at what value sigma becomes negative, or basically sigma prime becomes negative. So to see the nature of or the behavior of solution, for simplicity, let's take, so we have these two equations, but still solving them explicitly are not is not possible or too complicated. So we'll take two forms. One is addition of their squares, and one is their division or their ratio. So while taking the addition and the ratio, it comes out to be this as their additions of the square, and their ratio comes out to be this value. So now, as the ratio comes out to be these values, so talking about the equation 3, we know that x square plus y square equals to 1. This function basically represents a circle with radius 1, and we have something like x square plus y square equals to exponential of some value which is dependent on sigma prime and tau, which is basically a circle whose radius is exponentially increasing with sigma prime or tau. So for tau greater than 1 by e, the curve is open on the left, meaning that it converges at infinity, and it passes through 0 comma 1 and 0 comma minus 1, and these 2 points are crucial in our nature and the behavior, which will like in few time we'll get to know what is the importance of these points. And let's analyze the behavior. So let's forget the complicated graph on the screen or the complicated curve on the screen. So basically what we will do is, this is our circle, so we know this is our circle, and this curve is basically for this equation with the radius as 1. So now instead of 1 we have the radius which is increasing exponentially, so we will draw a curve for a exponential graph. That's it. So these two are curves for exponentials. This is for positive and this is for my negative exponential of minus 2 tau times sigma prime. And when we plot sigma, like omega prime to sigma prime, so basically what happens is, for the smaller values of taus over here, due to the converging nature of exponential, over here the circle will go somewhat like this, in like curve like this, and in the negative part it goes and converges at infinity. So due to the influence of that, our radius will be affected to the exponential, and as we know that exponential has the factor of tau. So this curve is for the smaller tau, but when that value of tau is very great or very large, so for the larger values of tau, the convergence point shifts to infinity. So this is how the curve will look like for larger values of tau. So basically for larger values of tau, this part shifts towards the origin, and thus the curve represented in red lines is basically the curve for equation 3. And now talking about the equation 4, we have this equation basically, and this equation can be again rewritten in the form as a function of like sigma prime as a function of omega prime. And when we plot sigma prime against omega prime, so basically we have this entity, and this is scaled by this factor. So let's plot this entity first. So when we plot a cosine wave, this is a curve like cosine wave represented in blue. So this is how our cosine wave is, and so this is basically how we derived, and this is where sinc function came from. So basically, like we rewrote the equation, the same equation, and we got this contribution in the denominator. And when we plot the sinc function like this, so this is a sinc function, and when we take ratio of both, so this is how our function will look like, which will go to infinity, minus infinity, and it will cut itself from minus infinity, and it will jump to plus infinity at this point asymptotically, and again it will start from plus infinity like this. So this is our function for this, and now we have to scale it with the factor of minus 1 by tau. And basically over here, yeah, when omega prime is equals to 0, the value of sigma prime is 1 by tau over here. But let's talk about it further. So we have to scale it by the factor of 1 by tau. So when we scale it by the factor of 1 by tau, so basically, yeah, this is what we are talking about. So when omega prime is 0, sigma prime comes out to be 1 by minus 1 by tau. Yeah, okay. So this is how the graph will look like. But now we have to rotate the axis of this curve and overlap it with the equation 3, because the graph of equation 3 was omega prime against sigma prime, and this is sigma prime against omega prime. So we just have to shift the axis and overlap this curve with the curve of the equation 3. So when we do this, so what we are basically seeing here, so let's consider the curves in green and black. So this green curve, let's consider this green curve, and this curve. So what is happening? So over here, this is the point minus 1 by tau, and this is the point pi by 2 tau. and it came from this. So now what happens is, as we know, here these 2 points are crucial, which are basically 0, 1 and 0, -1. And over here, these 2 points are crucial. So using these 2 points, we can analyze the nature of our curve. So basically over here, they are intersecting and giving the solution in the left half plane. And this is for the smaller values of tau. But when the value of tau becomes too large, so what happens is, as we discussed earlier, this curve shifts inside and this curve also shifts inside. So basically this curve, like this curve shifted over here and this curve shifted over here. So when these two shifts toward the origin, so now the intersection points shifts to the positive half plane. And as we discussed earlier, we don't want the values of sigma prime or sigma to be positive, because then our overshoot will go on increasing and we want a decaying overshoot to reach the steady state. So basically all the intersections and now we here is an intersection, the second intersection is over here, and we have infinite intersections, but basically all the intersections happens in the left hand side for the smaller values of tau, and we want that because we want our exponential to decay and not to increase. The higher values of solutions will die out quickly, and basically the solution is dominated by the first intersection or the first two intersections. So for longer, for larger values of tau, the solutions are in right half plane, as we discussed. And as we said earlier, when sigma prime becomes positive, the oscillations will not decay and we won't achieve stability. So this acts as a boundary condition for stability. And by here, so basically for the curve, for the curve of equation 4, to cut the y-axis, basically to cut the y-axis, so this is the curve, and for this curve to cut the y-axis below the value of 1, basically like this, the value, like it cuts y-axis at pi by 2 tau, that we know. So this curve cuts y-axis at pi by 2 tau, and now the value of pi by 2 tau, if it is lesser than +1, so basically this case, if it is lesser than +1, then the solutions lie in right half plane. So if this concept is clear, then we can set a boundary condition that we don't want our solution in right half plane. So basically what we are saying is pi by 2 pi must be lesser than +1 in order to shift, in order to realize our solution in right half plane. So basically when pi by 2 tau is lesser than 1 or tau is greater than pi by 2, instability occurs. And the solution to the differential equation, basically, let's talk about the solution, is nothing but v naught of t is equals to summation of k equals to 1 to infinity ak times exponential of sigma k plus minus j omega prime k times t. So why plus minus I say? Because along with positive, we'll also get a negative solution as well, the mirror solution as well. So, but we don't have to consider all the intersections of the curves and basically all the solutions, and we can approximate the solution by first intersection itself, and basically it will give us a1 exponential of sigma prime 1 plus j omega prime times t. So these are the lowest frequency solutions which are closest to the origin. And now let's talk about the boundary condition. When tau is greater than pi by 2, we have at least one positive solution, which brings instability. Basically, at least one positive solution which is in right half plane. So basically, this means that TD, if greater than pi by 2 times k by omega u, or pi by 2 approximates to 1.5. So basically, when the delay is greater than 1.5 of k by omega u, instability occurs. And now let's summarize the delays. So when we have small delays, it speeds up the response, and for TD equals to 1 by e times k by omega u, or basically tau equals to 1 by e, we get a fastest response without any overshoot. But for tau greater than 1 by e, but lesser than pi by 2, we get stable response with ringing. But for tau greater than pi by 2, we get unstable response. So that's all for delays in a negative feedback amplifier. And thank you for watching.